Hello, everyone. It is May 31st, and this is the libhal biweekly meeting. We skipped last week, and just because I was not able to do the meeting, but now we have some pretty big things to talk about. So the TLDR highlights just one thing to talk about, which is precompiled libhal packages in Conan. This is a pretty big step in the project. Let's get right into it. So I got this I got this reply back from ChatGPT. Basically asked it what is a precompiled library, just so I can get a decent definition. I think it did a pretty good job. For everyone here, if you don't already know what a precompiled library, it is a precompiled library, also known as a binary library or pre-built library, is a collection of pre-compiled code and data that is packaged for reuse in software development. It contains precompiled functions, classes, or modules that can be linked and imported into a software project, allowing developers to leverage existing functionality without having to rewrite or recompile the code from scratch. Oh, and as I'm going through this, please unmute yourself. I'll be able to hear you unmute, and you can start talking. There are going to be some areas in here that may be a bit confusing, so if you have any questions, I encourage you to ask them, because I want to make sure that people who are watching this online, if they couldn't get the opportunity to ask a question, and I can't get back to them on the comments, maybe someone can ask the question in person and they can get their question answered. Now, why move to precompiled libraries in general for C++? Well, number one, faster compilation times. When your project grows in size, compiling your C++ code base can become time consuming. By using precompiled binaries, the compiler has less work to do because portions of the code have already been compiled. It doesn't need to parse and compile the same headers over and over. Consistency. With precompiled binaries, you can be sure the same code will be compiled in the same way, which can reduce inconsistencies between different environments or build configurations. Just a little note here. GCC and Clang's pre-built libraries can work with each other, but not all compilers can work with each other. Like MSVC, Microsoft Visual Studio, Visual Code, does not work with GCC. But you can at least be pretty certain when you use GCC with Clang or vice versa that the code that was compiled and the symbols that were made in your pre-built files will look the same in however you build it, unless you use link time optimization, which is another area we're not going to go into too much here. Maybe in a future meeting. Next up would be code distribution and updates. If you're distributing your C++ code, you may not want to give out the full source code or require users to compile it themselves. In such cases, providing a precompiled binary is much more user-friendly. More on this later on. Updates to the program can also be handled by replacing the old binaries with new ones, without requiring the end user to handle the compilation process. And this is kind of that core of what Conan does. It really just provides you with the header files and the pre-built binaries, not having to care or worry about the compilation process. And then lastly, protection of intellectual property. Precompiled binaries are much harder to reverse engineer than raw source code. If your C++ code contains proprietary algorithms or trade secrets that you don't want to expose to the public, distributing it as a precompiled binary can provide an additional layer of protection. Just a note, just to be transparent, this was also generated by ChatGPT, including also the emojis. I asked it to put in the appropriate emojis for each one of these. But I kind of gave it a lot of leading questions to have it give me this output. Now here's the part that I wrote myself. Why we are moving to precompiled binaries. So first things first, faster compilation times. I know we already talked about this, but I want to give some anecdotes. When you're working on a team where the compile times are greater than 1 minute, it becomes very noticeable and very problematic. If you can compile something and it gets compiled within a second, you can be very productive. You can iterate quickly. You can test things quickly. But when you have something that takes more than a minute to compile, you will start to, get distracted. You'll be on Instagram Reels, you'll be, reading a book, you will be, looking up something online, you'll be preoccupied with something else. Not exactly a bad thing all in all, but it very much becomes a problem when you have deadlines to hit. So the other thing I want to bring up is what long build times do to productivity, velocity, and morale. When it comes to productivity, Well, the more time you have to spend compiling code, the less time you get to actually test things out. When I was at Google Assistant, we had some build times that were upwards of around 45 minutes. Well, I'll say one more thing, which is that it's not just the build time, but also the time it took to deploy it. But I believe deploying it didn't take as long. So 45 minutes of compile time is pretty insane, meaning that like I just shoot that off and then I can go work out, which I did do. I could go get some food. I can go on a long walk and then come back and get my stuff done. But it made my velocity on my project a lot slower because I only had a limited number of compilations before the day's over. And what this affected was my morale. When I needed to get certain things done, I really felt like I couldn't because I just didn't feel like I had the opportunity to test and play around and really explore the code. I had to be very certain that whatever I was doing would work because otherwise I'd have to wait somewhere between 20 minutes to 45 minutes before I can actually do anything and test it out. I came up with schemes and methods to fix this problem by basically parallelizing out different features into separate builds and then building them all in parallel. And whichever one would finish first, I would test. And then when that's done, I would then go in, edit it, run it again. But that doesn't always work for everything. I was kind of lucky with the way that the software was built up that I could do that. Not all projects can be that way, and I don't think libhal projects will be that way either. Consistency. Now, I believe that your compiler is going to do a decent job of recompiling your code to make sure that if you compile it nearly the same way, it shouldn't really be affected. Even between compilers, the actual code gen will probably be better and safer, not like worse or give you weird code gen or give you errors. But having pre-built binaries is something that the industry not only wants, but is what they expect. This is important. If we go in there with just saying, hey, we use header-only libraries, and that's what you're going to have to deal with, there is this sense in everyone's head that, header-only libraries, that is for individuals who can't get their code to work with their build systems. That is, not having pre-built binaries means that now I have to consider how often I use this code and will this cost me compile time? As well as also this overall sense that the code can change very rapidly and will also cost me a lot of compile time, but also not having that feeling of consistency. So overall, the C++ and the embedded community expects to have pre-built binaries, so we need to provide those for them. Next up, we have code distribution and updates. When I started, and I'm going to show you what the code looks like for LPC and libhal now when we get an opportunity later on. But what we're really going to be doing is trying our absolute best to ensure that the header files do not try to include as little implementation detail as possible. Why? Well, there's something that I noticed. We put all the implementation into the header file, and there's ways to protect the implementation so that developers cannot get access to it. And I was very liberal about how much we exposed, so that, I think all the information should be exposed so that people can leverage it however they need to. Problem: if someone starts leveraging aspects of the API or register map or something like that, and we decide to alter it and or move it somewhere else, we break them. Basically, moving a register map somewhere else, let's say to a common file or something like that, is an API break. And then I realized that there are so many different vectors and things that could basically be an API break. By doing header only in the way that we did and making everything so liberally accessible, we made it very difficult to not break the API when we try to make modification to things. So, in order to ensure that we don't keep pushing out API broken or basically have to keep bumping the major number for our packages and our libraries, causing our clients or any one of our customers or anyone that's our users to look at that and go, well, I don't know if that particular new change is something that I can bring in because it breaks the code. I got to go do more work to fix this particular requirement. Now I'll stick with the old version. This will help us to allow our code to stick with the old version. And lastly, protection of intellectual property. This is a requirement if we want to go beyond the open source community. If we want to go to the closed source community, there are going to be people who are going to want to make money off their code. And there's nothing wrong with that. So if you want to, let's say you built like this mech suit type application software, but you don't want to give that out to everyone. You want to keep the source code to yourself and distribute out the binaries. If someone wants to make that, this allows them to do so. If we do header only completely, there's no way to really protect the code in any reasonable way. You really do need pre-built binaries. And if you want to get even more extreme with it, making sure you strip out all of the debug information out of the binaries as well, so that like you really can't, you can try to disassemble it, but it'd be pretty messy and pretty difficult to discern what's happening. So yeah, if we want to make a marketplace, if we want to support our proprietary users, we're going to definitely need precompiled binaries. And the above here will be focuses of libhal going forward, making sure that we focus on faster compile times, not just keeping the binaries, the binary of the code smaller and keeping the object size smaller, keeping the code efficient, but also making sure that the compilation times are fast, that the code is consistent, that we have a really good user experience for code distribution, and that we have a pathway for users to build IP, build code that is proprietary. So I realized as I was writing these slides that not everyone knows how code is compiled in C++. So I wanted to give a bit of a primer to it. So in the process of making an application in C++, generally you have a couple of things. You have source files, your CPP files, your header files, your .hpp files, and you have your libraries, your archive files, or other object files. Now, what you do is you pass your files through a compiler. That's what the C stands for here. Also, you then pass the location of the headers to those compilers as well. Headers indicate, and you guys probably already know this, but indicate your API, your public API, what things you want to expose from your source files. Now, technically, you never needed headers at all. Headers are not really a requirement whatsoever in C++. What you could do is forward declare everything and extern declare everything. That's a disaster, though, because it could be very easy for you to typo that out. That's why we have header files. Good old code reuse. Now, when you pass your headers and your source file into the compiler, out comes an object file. You pass the same headers, or maybe depends on what each one of these requires, but you pass a set of headers to each one of these different files, each one of these different compilation units for each one of your CPP files. You then get all of your object files, and you then take all your object files and you throw all of them over to the linker along with your libraries. The linker does the work of taking your linker script, which is a way to lay out the actual binary, all of your object files, which include compiled forms of your code along with metadata, and your library files, your archive files, which also are basically stitched together object files with metadata attached in as well. You take all of that information, you put them all together, and the linker does the job of pretty much linking all the different parts of the project and the application together. One thing I'll say, for those who may not know this, when you have a header file that doesn't have a definition, it becomes an IOU when the compiler sees it when it compiles code. If it goes, oh yeah, there's some sort of printf function that exists, it doesn't need to include the actual printf definition. It needs to know that there's some API like that. So it keeps an IOU in the binary. The linker is what does the job of saying, hey, here are all of the IOUs, and here are all the other symbols. I'm now going to find and map where all these different things go, and once I have that, I'll then position them in the right locations and then give them solid addresses. That is how compilers do for C++. Now, in general, this process can be done with a bash script can be done in Python, can be done in CMake, can be done in Meson, can be done with a lot of different languages or systems and projects and applications. So this is pretty much the generic way that happens. All the other build systems are pretty much doing this same thing, except with more features. And again, if you have any questions about this process, please just raise your hand and I can go back to the slide and we can talk about it. Now, how do you precompile your code? Well, the first step is to take G++ or whatever compiler you're using, use the -c flag for G++ in this case. You give it your source file or your source files, and it'll spit out a bunch of object files, either with the extension .o or .obj. You then use the archive command to then take all of your object files and put them into an archive file. And that's pretty much it. Those are 2 steps. Now, how this gets done in your build system or with your code, that depends on what you're doing. This is very simplified down, but that's pretty much in a nutshell what you do. Oh, and a little bonus note, back in the day when I was working with archive files and playing around with them, I did find that that you can't just combine multiple archive files. If you want to kind of make a big conglomerate of archive files together, you have to use the archive command to split up your archive file into multiple object files, then take the whole group of those and bring them into another archive file. You can't just kind of stitch 2 archive files together. It won't understand how to handle that. At least not at the moment. All right, so this process looks almost identical to what we showed before. This is the extended version of how to precompile code. So it's a similar process to building a static library. You take all your source files, you pass them through your compiler, you get object files, you get your other libraries, and you put them together with the archiver, and out comes your library .a file. Same process, just except that you use the archive versus the linker. Now, how are precompiled files used in C++ projects? Let's look at, let's say, some application for using libhal. Yellow indicates header-only libraries. In this case, libhal and libhal-util are very thin layers, and libhal is necessary to just it's only going to be headers. There's no reason why it would ever be source code, for the most part. Libhal-util, for the most part, should mostly only be used inside of source files, so you're not really going to worry about it taking up too much space in the header, although I am looking into potentially moving libhal-util into a pre-built binary. Yeah, when you actually build up a project, you're going to see that what we actually end up exchanging are just the header files for the libhal ESP, libhal ARM Cortex, libhal RMD, LPC40, STM32F1, and their archive files, and whatever headers that come along with them. Then you compile all the files that you need for your application. You then link all your objects in along with all the archive files, and bada boom, bada bing, you have your finished application. But rather than having to compile all of the files inside of ESP8266 or ARM Cortex or RMD or STM or LPC40, you could just take these archive files from the package repository when you go and download it. And if it's already cached inside your local server, inside your local in your machine, then you don't need to ever do that again unless you change the version number or something like that. So that's pretty much how precompiled files are used in C++ projects, or at least our projects. And this little line here basically says that this application not only uses maybe LPC40 or very likely LPC libhal STM32F1 separately, but also will use libhal ARM Cortex directly. Now, here's what happens when you do what we were doing before, using only header-only libraries. What you get is you have a bunch of header files all over the place. You don't have any library files, and you have to shovel all of these through your compiler for it to do its work. Now, currently, our code is pretty small. We don't have that much code, so it's not the biggest deal. But when you start adding more and more and more and more and more header files to your project, you start to get slowdown. Mostly because your compiler has to evaluate your header files every single time it runs any instance of the compiler. Even if you use multiple threads to run multiple instances of GCC, or Clang or whatever else you're using. Every single one of those instances has to look at the same files and reevaluate them. And evaluation is effectively compilation. Actually, it is compilation. So you basically are recompiling the header files n number of times, where n is the number of source files that need to look at them. And without any libraries, there's nothing really, you pretty much have to put everything through your object files here and then link it all together. So this ends up causing a lot of slowdown at the compilation step. Linker step doesn't take any longer than it normally would, but the compilation step ends up taking drastically longer. So it's problematic. Ends up making things slow. As cautionary tale, if you ever use the boost library and use I forget what it's called, like level 5 boost libraries, which have a lot of dependencies below them, it takes a long time for any of that code to basically get compiled, because boost is completely, if I remember right, could be wrong here, but I'm certain actually of this, that's completely header only. That's because they wanted to be able to make it deployable to anywhere, which is a great idea. I mean, I get the rationale. I did the same thing. But people complain about and avoid using boost like the plague for maybe some other reasons, but also mostly, well, a good reason I've heard a lot is because of the compile times. Because the libraries are so large and they include so many different things, it just ends up slowing down your compilation process dramatically. So that's kind of the problem with using compiling with header-only libraries. Now, what happens when we're using pre-builts? What we can do is really reduce down the size of the header files and really increase the libraries. Now, the cool thing about this is that now for all these different parallel operations, they're a lot faster because they don't have to evaluate as many files every single time. Just the source file and whatever little bits of information are inside the headers. The libraries only really come in during the linker time. Now, most linkers are, I actually don't know if I can make this claim, but usually linkers are single-threaded, meaning that once you hit the link stage, it takes a while. I remember on Google Assistant, it was actually that way. Compiling, we had like big old servers to really blaze through compiling everything. Like we have like hundreds of threads going out and compiling as much code as possible. Once you hit the linker, though, that's when things stop to a crawl, because now only one core can do all that work. There is a linker called Mold, modern linker. I don't know where that project's at, but they have figured out a way to parallelize the operations, which is awesome. It has some really great. Oh, I think also Gold maybe does that too. Gold's another linker. But yeah, after that, you then can build your application. It's a lot faster. So, and some of these files, specifically this one here, is actually kind of changed a bit. But we have some new files. Precompiled and libhal. Now, for a lot of libraries, we now have a source folder, and we now have a CMake lists file in the root. And then for processor libraries, and also, this actually should say processor and platform libraries, we now have Conan directories. Now, I actually want to show you what this ends up looking like. So let's go here. Let's get rid of some of this stuff. I'm doing some CI stuff right now. Close all. Let's go to libhal LPC40. And let's look at a diff real quick. So let's look at ADC as a very small example. And let's click on this. And we can see just how much this is all code that's been removed, how much code has been removed between the two. Yeah, just gobs of code. And this is one of the smaller libraries. Like if we go to can and do the same thing, you'll see just like how far it goes before you start seeing common code. A little bit here, a little bit here, and then everything else deleted. Now where did all that go? Well, it went into the source directories. Here, we'll be able to find, let me actually zoom in a little bit so it's a little easier for everyone to see. We can go over to, let's just do ADC for now. You can see all the different code here. Actually, let's actually show you the header right now. So the header only really includes very few includes here. And before we had a whole bunch, we needed every single thing possible in order to make this thing happen. Now with separating things out, the ADC HTTP file only really needs units. Actually, I think I could probably remove units. No, units is for hertz here. ADC is to get the ADC interface. Constants, which are constants that we are making available in the public API, such as what are the peripheral IDs, as well as also IRQ numbers for things. And the pin mapping, which is necessary to have this pin object be here. That's pretty much it. You have a get function, you have a construct custom, and that's about it. And then all the implementation details have been brought into the CPP file, including anything else that's necessary to make it work, in order to generate the, in order to write out the setup operations, like powering things on, that kind of stuff, as well as also the getter function here and how it operates, and sampling and the constructor and everything like that. Even though a lot of constructors are pretty small, it's in our best interest to simply keep them inside the source files, just because we may want to expand them in the future. Just keep as much detail out of the header file as possible. We also have these extra header files, which are only inside the source directory. These are helper header files that are not exposed publicly. They're only used to facilitate and make it easier operations and like helpers and utilities and that kind of stuff for like this particular package, the LPC package. And actually, I just want to check this real quick. I need to put myself as do not disturb. Okay. Yeah, so we have the ADC register here and some of the control flags here. I am considering very strongly to move over to BIF fields. We discussed this last week, or not last week, but the last time we had our meeting. But for now, this works, so there's no reason to, this is a refactor, not really trying to redesign everything. So that's pretty much how the code looks. Here we actually have to do the work of building the library. So this requires us to use CMake or whatever other build system you're interested in, find the necessary dependencies, add in the test code. We no longer will have a Conan file in here. We will just have another CMake file that knows how to test out the code. Or basically build the binary to test out the code. Bring in all the source files, any commands that are necessary, and then also install. This install flag just knows how to install headers and that kind of thing in the archive files in the appropriate places. So that's what we've now added into libhal when it comes to pre-built binaries. So now you have to kind of manage the code between the interface, which is the include directory, and the source directory, which is the actual implementation. Now, because of this, we have to get rid of tweaks files. You might be wondering, well, why? Well, the reason why is because tweak files really only work for header-only libraries. You can't, when libhal LPC40 gets compiled, it does not know what your libhal tweaks file was set to. Because what happens is you usually build your dependencies first, then you build yourself, and then you add your dependencies in. By the time you've built the LPC stuff, there was no information about the libhal tweaks to change it. So basically, because we're moving away from having everything header only, the tweaks file no longer works, meaning that we have to utilize other methods to tell our packages what things we're using at what time. That process I'll go into a little bit later. Actually, there should be a slide for this. Another thing here is the source directory. This is where all your CPP files go. This is where any helper internal register headers go. Consumer won't typically want these, and we should not give them to them. But we may give register information to the user if we end up wanting to allow for things like core or peripheral dumps. But this also could be implemented through GDBs, so it may not be the most useful thing. And it also shows a focus on the smallest useful exposed API as possible. We really want to make sure that our APIs or header files just don't include any more information than they really need to. And this can help us to prevent and reduce our chances of API breaks. And a little live tour is pretty much what I already did, so not really much else to show there. Let's see if there's anything else I can kind of show. Oh, here's an example of something that I was talking about before, which is libhal util. None of the headers should include util unless those headers are doing some actual work. You have implementation inside your header. Otherwise, the utils should only really exist in the source files in order to help the source files out. But yeah, no, just everything you need in order to basically all the implementation details necessary in order to get everything running. Let's see if there's anything in particular that stood out here. There is one thing in particular that I am considering right now, which is rather than having a getter function for these objects that which get replied sent back, I'm actually going to make a get 1, get 0, get 1, get 2, or like port 0, port 1, port 2. I'm thinking about redefining what get is so that we might just move away from get and use things like ports or pins and give the names so you can get static references to things. But there are going to be certain cases where that doesn't make sense, such as GPIOs and that kind of thing, where there's going to be too many pins to write out a getter for each one of these. So that's for later on. Probably next week after I figure out more things with CI and how to keep the system, how to really manage pre-built and precompiled binaries better. We'll probably start going into that as well. Yeah, so that's pretty much the source directory. I went over CMake lists, so we don't have to go over that here. But basically, CMake lists knows how to compile the package for, I say the host target, but I actually need to be more clear. Just for whatever target, or actually, in Conan, the host target is the target that executes the code. So in this case, it's either for your laptop or your desktop or the microcontroller you're programming for or the Raspberry Pi you're programming for. But it knows how to compile the package for your host target, what files it needs, what headers it needs, what packages it needs, all of that. The CMake lists also must handle compiling unit tests if they're on a machine that can actually run them. So in this case, if you try to compile the code for your microcontroller, the host testing stuff will be skipped because that's not really relevant or useful, and the compiler won't be able to compile our host test because it won't have support for things like threads and exceptions. And the CMake list should be as simple as possible and not be concerned about a lot of things like certain compiler flags or the system that you're using. Let Conan and its mechanisms handle all of that for us. Now here's the big difference is Conan profiles. In Conan, a profile is a configuration file that specifies the settings and options for a particular build environment. It allows you to define different sets of compiler settings, target platforms, build options, and other configurations. Profiles are incredibly useful for managing dependencies across various build environments, ensuring consistent and reproducible builds, and facilitating and collaborating between developers working on different platforms. Before, with header-only libraries, we could rely on applications and recipe to set the compiler and options. The options in this case being set up through the tweaks file. With pre-built binaries, if a pre-built library file does not already exist based on your profile settings, then all packages will need to be recompiled. This can only happen if we globally set the compiler, settings, and options. And the only way to do this with Conan is through profiles. As an example, what we did before, or what we're currently doing with the robotics team, is that they will embed the compiler that they're using into their either Conan file txt or their Conan file pi. That works so long as that is only required for your particular application. It only works for header files because you have to recompile the files anyway. But the recipes in Conan will not know what architecture you're trying to use when you compile. So you'll need to basically compile down the code for every single one of the architectures that you plan to support. So, and profiles are basically globally known. So when you use a profile, when you do Conan create or Conan build, it will look at that profile for every single instance that it creates and every single time it builds something. Whereas if you just had it just for your application, it'll use its own host compilers for all the other packages, and only for your project will it use your compiler, which will cause you to run into architecture conflicts when you try to link everything together. Here are how some Conan profiles look. So for LPC 40, we have this very generic one. This actually isn't up to date. There have been a lot of changes since then, but basically we have our settings, our tool requires saying that we need the ARM GNU toolchain, some options to set like platform and stuff like that. Setting the CPU and float ABI, although this is no longer something that we do this way. Your build environment variables, one new one that's going to be consistent around is the build environment libhal platform and libhal processor library, so that the build system can identify, oh, we're doing the X, Y, and Z. We're working with this particular platform. I should change my behavior accordingly. And then as well as also C flags, C++ flags, and linker flags. This is like the common one, and you can use Jinja templating in order to include stuff, in order to set variables, that kind of thing. So we set a couple variables, then we include this template, and then it fills out all of the other items here. And to actually show you what that looks like now, here we have Conan profiles, then we have just LPC 40. We have that, we specify that the compiler is GCC because we're going to be using the ARM GNU toolchain. This is our default. We don't support Clang at the moment, so there's no reason for us to have a profile for Clang. And if you did want to use Clang, you can override these in the command line or also copy these profiles and use them yourself. Yeah, there are options, so you're not really stuck with what we choose here. So compiler GCC, C++ standard is 20. The standard library is lib standard C++, version 12.2. The OS is bare metal. The architecture is STUM v7EM. Just a little note here, this does not exist currently in Conan. You have to add in a special user settings. I'll be adding in all the steps into the documentation so that you won't have to know all this extra detail. But me and one of the other, I believe someone who actually works for Conan, actually works for JFrog with Conan. We're currently working on a well, not even a pull request, basically an issue to discuss it. But at some point, we're going to make a pull request to add these fields to the global Conan settings, so that you can actually build projects with these and not have to worry about bringing in other user settings. Tool require specifies which compiler we're using, so we are actually using this compiler, and this will be known for all builds that use this. Our option is just setting the platform name and then also setting these build environments. And you can see how these look here. And you actually see that like the CPU is Cortex-M here, the float ABI is soft here, and then the platform name is LPC 4072. And then something over here where we have the float ABI being hard, and then we have the platform is 4088. Now, what's new for developers? So old packages will still work as they have been before. We're not deleting them. But to compile a libhal project, a profile argument must be specified. A platform libraries now have Conan profile directories. And don't worry about memorizing all this stuff. There is a README for this stuff. So there'll be like a Conan config install with lpc.get, Conan/profiles, and then you specify that you put inside your profiles directory. Same thing with STM. But the READMEs will have like, oh, copy these things in order to get all the profiles. Now what will happen here is going forward, rather than just doing Conan build dot, or adding the, like sometimes you add in the build type, sometimes you add in build missing, you'll also need to add this additional flag, PR. After you've done this step, you've installed all of the Conan profiles into your local cache, meaning that you can access them without needing to give them the full path. So if I want to build my application for LPC 407074, I just specify my profile as such. I also specify which build type I have. Notice that this one does not specify the build type. That's because I don't know what you want. And I'm not going to assume that you want the most optimal. You may want to do a debug build. You may want to do minimum size release build. I don't know what you want. And this -B may start to go away as necessary because we're going to start really pre-building everything. Whereas before, even though you actually didn't really build anything, the way that Conan was operating, the way that we were using Conan, made it think that it needed to rebuild the headers each time. So something to keep in mind. And if you ever needed to build your own profile to extend it or change some items up, you can always just simply include the profile now and then start editing your settings. And every time you rewrite a particular setting, it overwrites the previous one. So you can override things as well if you wanted to with this and keep all the parts that you want to keep. But yeah, as far as anyone in robotics or pretty much anyone else using libhal, the only real change here will be that you need to specify this PR when it comes to building. Now, what's new for developers? Factory functions no longer take template arguments. They now take runtime arguments. The documentation will explain the documentation and the result T from boost leaf mechanism will basically allow you to know if any errors occurred. Basically, we don't get compile time error checking, but we do get still error checking. But I'm actually thinking of ways where we don't even need either one. We just simply give you the APIs that you need. For example, if you're going to be using I2C and you only have let's say 5 to 10 ports, there's no reason why we need to use template and static asserts. We can just simply have 10 API calls. And whenever you grab one, it'll give you a Meyer singleton object. It'll initialize it at that moment and then give you back a reference to that object and you start using it as you need. Oh, sorry. And then everything else pretty much stays the same. So basically, factory functions go away as they are. They're still going to be factory functions, but they won't be the same. Next up, we have managing multi-platform applications. Because we no longer use header only, each platform will need to use a new environment variable to set the target library. So if I go over to libhal PCA demos, we can see an example of this. Now, I have not worked on PCA demos for a couple, 4 or 5 days. So this probably is not working completely. But here, you can actually utilize the libhal processor library and libhal platform environment variables in order to just slap it into the libhal : your processor library. That way, this particular project can build for it can basically build for any arbitrary platform. It doesn't really matter, really, so long as you also have the code that knows how to map to the hardware map. But yeah, no, it doesn't really care. This makes it a little bit more automated, so you don't have to have one of these for every single type of device you want to potentially support. Although you will need one of these, so not sure if it benefits us still, but maybe it could be even more automated. Another thing as well, just a little helper thing, to take the options platform value and to add it to the build platforms, the platform directory in CMake. What that just does is when you go to build, it'll say LPC 4074 versus just overriding min size rel. So it basically makes it so that you can have binaries for all of your different platforms you want to support, and there'll just be more directories in this area. So that's the little demo for PCA showing off how you can basically build for anything. You'd also need to include options platform any as well as default options platform unspecified. This is basically just a way to make sure that when you do use those profiles, that they do pick up on the platform. That's why here you'll see that it actually has an asterisk here. This is saying that this particular platform variable needs to go to all packages that basically support it. All right, so let's see. We're almost done. It's the last slide. Necessary work going forward. Migrate repos and packages to rebuild pre-builts. It's going to take some time. It's going to be some effort, but I am certain we can do that. Investigate pre-built strategy for device libraries, processor libraries, platform libraries, and application libraries. It gets a little wonky for, well, I don't know. I don't have a solution yet, the cleanest solution. And I've been going down one route, and I don't know if I should turn back, but I'm trying out a lot of different ways of handling a lot of this. But the idea here would be that device libraries will, I hope to have a single CI step that it can include that will produce pre-built binaries for all of the chips that we currently support, all the architectures that we currently support, all the Thumb ones, all the RISC-V ones, any Raspberry Pi ones, etc., etc. Processor libraries will need to consider the settings user YAML file as well as all available architectures that they may support and building for them. Platform libraries, build all possible target platforms and also set your processor settings. And then application libraries, same as device libraries. So we're going to continue working. Currently, there is a PR to bring in ARM GNU toolchain into the Conan index. It is still under review. I'm hoping that in the next couple weeks, it will make some more progress. We can get it in. And then we can also then close and sunset the ARM GNU toolchain repo that we have in libhal. And then also, like I said before, they're also working to add ARM MCU specific default settings to Conan. And then maybe later on also adding in all the RISC-V ones as well. And yeah, just so you know, the libhal ARM Cortex is now ready for pre-built. LPC, because I'm still working through a lot of the CI strategy stuff, has not been finished up yet. I'm currently blocked on CI being broken for liblpc for the new PR, for the pre-builts. So I'm still trying to figure out the best way to go about handling it, and it'll take some time to make progress in that regard. But once this happens, the documentation needs to change because otherwise the current documentation will not work. And I do hope to do version control for the documentation so that if you want the previous way of doing things, you can go back in time and look at the previous versions of the documentation. So I'm working on all of those currently. Any questions, comments, concerns? Awesome, awesome.